Right, so welcome to today's kind of introduction to the concept of waves and electromagnetic radiation and how those sort of relate to our study of the atom, because they kind of do and they kind of don't. This is sort of a foray into some physics for a little while, which is kind of fun just to get out of the realm of chemistry and reactions and all that stuff. But in the end, that this is going to give us some information about how atoms are actually put together. So this kind of feels like a sideline, but it's kind of cool stuff to talk about. So it gives us more information about the internal workings of atoms, I guess, if you want to think of it that way. So here we go. In terms of what is an atom, all this sort of stuff. When we're trying to study atoms, because atoms is what chemistry is all about, they're kind of tricky little buggers to try to do work on because they're just so dang small. And then furthermore, they tend to move really, really fast. And we're huge, and we don't have tweezers that small. So we have to use a lot of really indirect methods to learn about something as small as an atom, even as small as reactions and things like that. So we have to use a variety of different techniques to be able to learn more about kind of what these things are and how they work together. We have to pull together lots of different kinds of information and lots of creativity to try to figure out how we can detect something that's basically undetectable, too small for us. Way back when, in the early 1900s, so this is a long time ago at this point, people were just sort of trying to figure out the various bits. Like, we know there's electrons, we know there's protons, we know there are these things called atoms, we know what the nucleus is, but sort of how are they assembled? There's a bunch of different crazy sounding models at this point about how they're put together. We'll talk about plum pudding and blueberry muffins and a variety of other things here in a couple days. But there were some of these early ideas that as we had images for what we thought an atom was or how they were put together, we continue to sort of revisit and revise what we think that particular idea is. And we call these things models. Like for right now, based on the evidence we have, we've got this sort of picture in our head for what we think an element is, or what an atom looks like. Models come in all kinds of shapes and forms. We typically think about like physical models, like I've got a model car or a toy or something along those lines. But in science, we could say build a model of the solar system to see how big the planets are or how far apart they are. Or you could build a model of a volcano to see how the rocks go together, or models of like earth layers to see what earthquakes are. So sometimes we do physical models to figure out what they are. A lot of times we do more conceptual models, and this is kind of what this is today. Conceptual models are more like diagrams or pictures or images. Graphs sometimes are a type of a conceptual model, a way for us to kind of get our brain around to draw a picture of something we can't really see. So anytime you draw a picture of an atom, it's got to be a conceptual model, right? This picture up here in the right corner of this thing, that's a conceptual model for what an element could look like or what an atom could look like. There's also a bunch of different types of ones called mathematical models. Mathematical models, when we use equations to predict systems. An equation is just a way of us to sort of understand or predict a system, but that math itself isn't the real thing. We're trying to actually get a picture of what's going on inside the beaker, so to speak, or inside that physical system. So these are all models. And models have strengths and weaknesses to them. One of the cool things about models is that we can revisit and revise them over time. This particular model of the atom, for example, is a very classic model. It's called the Rutherford-Bohr model. A lot of times we just call it the Bohr model. But it's named after these two dudes, Rutherford and Bohr, that were kind of alive in the early 1900s, trying to figure out how did things go together? What are the parts of an atom? So there's two main components of this particular model. That you've got a nucleus in the center, that it contains protons. Later on we also found out that neutrons were in there as well, but there's this dense central part. And then we knew the electrons weren't in there. The electrons were somehow outside. And in this one you can see that each electron sort of has its own unique sort of orbit as they kind of go around with one another. And we've been revisiting this model and for years, and obviously it's still a classic picture. It's a classic model for what an atom looks like, even though there's lots and lots of errors to it, which, you know, it's fine, we learn. Couple questions that aren't terribly well answered by this particular model that Bohr himself was working on is, how do the electrons actually move? Are they in circles like this? Are they at 90 degrees to one another? And then a second one, kind of an obvious one, but a second one was, why don't the electrons just crash into the nucleus? This is one. I'm not going to answer that particular question, by the way. But if electrons are negative and the nucleus is positive, shouldn't they just stick? Right? So these aren't answered by this particular model. Some of the weaknesses of this, but this is kind of the mindset that these guys were in when they were working on this particular model. It's like, how does this really work? Is this a good model for how atoms work? And it turns out, kinda is the answer. Bohr gets better as a result of this lesson. We'll see what he does. So models as we've got them are never perfect. They're kind of the best model for right now. It's sort of it's a good enough picture. It's like, okay, I get it. It's kind of a picture, but we always know that models need to be revisited, revised as we're collecting new evidence. Models should be able to kind of give us some predictions in terms of how the world is sort of put together. And then we can kind of make experiments to test those predictions. Does the model work or does the model not work? And typically, as they're collecting these evidence, they're sort of always putting their ideas into three big zones here. Yes, hey, I collected some new data. It exactly fits into the model the way I thought. Perfect, right? And that's great. That confirms your model, and that gives you some idea that maybe that model is pretty good. Then there's a lot of ones where it's like, yeah, kinda data, right? It sort of fits, but maybe doesn't fit as well as we'd like. So we might hang on to that model for a little while longer. Like something just isn't quite right about it, but it's still pretty good. We just got to figure out tweak it a little bit, right? Just kind of revise it just a touch. And then sometimes, man, we get some new evidence that goes, whoa, not even close. Man, we were expecting it to be this, and it was like way over here. That's when we really have to start revising, like throw that model out and start over. When you hear things about string theory and black holes and Big Bang theory and all this kind of stuff, sometimes those come out of that huge idea like, wow, that model doesn't work the way we thought it does. We need to come up with something different, a different explanation to kind of try to explain our results. So what we're going to take a look at through here is kind of how Bohr and the guys around that time were collecting evidence that led them to revise their model. He was looking at that atomic structure, sort of like the pictures up there, and he started to collect information about light and energy absorption, energy emission of different kinds of atoms. And he started to realize that his model was good, but that it wasn't great. His model kind of was okay with certain things. He could make some predictions that seemed to work, but in the end, eventually he had to kind of revise his idea of what he thought electrons did. And that's kind of the end of this whole lesson here. So anyway, what he did was, like many of us, let's burn some stuff. See what happens if I run electricity through it. Yeah! He found out that if you run electricity through particular elements, this is a gas discharge tube. It's basically a big long glass tube. It's about this long. I'll show you some in class. That it contains an example of, or a sample of just pure, in this case, hydrogen. And when you run electricity through it, it glows. And it doesn't glow white. It glows this really kind of weird pink color in the center, sort of bluish off on the ends, but definitely this bright pink in the middle. Well, why is it? Why is it pink? What is it about hydrogen that makes it that color? And why do other gases give off different color? For example, neon, when we do this exact same thing, gives us this bright red, like a just super scorchingly red color, and mercury gives off like a very cold blue color. Why are they different? And then what does that tell us about what's going on inside the atom? These are kind of the mindset that he's going through. Something funky is going on here. Does my model fit with this? And how does my model work with these new funky colors that I'm seeing given off? So in order to do this, we've got to back up a little bit. I'm going to answer more about this emission spectrum in the next lesson. Right now we're going to kind of focus on, well, what's going on with light anyway? We need to know kind of what it is. So number one, light is a type of energy transfer. So don't worry about it too much. It's like we know what it is, but nobody knows what it is. It's energy transfer. You feel energy transfer a lot of times in terms of heat. Like if I hold my hands up to light bulbs, you can kind of feel that warmth coming off of them. The more general term for light is something called electromagnetic radiation. It sounds scarier when you say that. We just usually abbreviate it as EM radiation. This is radiant energy, energy that can travel through space, and that can sometimes travel through certain types of material like glass and water, right? And that it does transfer energy from one place to another. So here's some examples of electromagnetic radiation. Visible light is a type of electromagnetic radiation. Travels through space, transfers energy. But here's some other ones. Microwaves. And I'm not talking about the actual appliance in your kitchen, but the stuff that's magic happening inside that appliance that makes your food cook with basically very little heat and very fast time. X-rays, another form of electromagnetic radiation, right? And the word radiation kind of makes more sense here. It doesn't look like light, it doesn't actually glow, but yet it can transfer energy, and we know that it's dangerous, right? Because it's X-rays. We have to wear that lead thing when we go in there. And then even radio waves. And I'm not talking about the kind of sound that comes out of a radio, but radio waves, the way that the radio actually gets broadcast over the airwaves, right, to get to your radio in the first place. These are all different types of electromagnetic radiation. Only one of them that we can actually see, and that's visible light. The other ones are all in that same type of stuff. They're just outside the ability of our eyes to detect what they are. In order to be able to differentiate between these different types of electromagnetic radiation, there are some things, the ways that we characterize electromagnetic waves. And these all act like waves. So they've got some certain characteristics. Like number one, there's amplitude, there's wavelength, there's frequency, and then there's something called speed. So we've kind of talked about this in class a bit, but wavelength is basically how wide the crests are from one another. So we take a look at this one right here. That's a short wavelength. The one at the bottom is a longer wavelength. From peak to peak is a little bit wider. That's wavelength. Well, going along with wavelength is the concept of frequency. How often are those crests sort of passing a particular spot. So this top one is a really high frequency, tap, 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 tap. This bottom one is a longer, lower frequency, tap, 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 tap. So wavelength and frequency go together. The longer the wavelength, the lower the frequency. The shorter the wavelength, the higher the frequency to it. And they're related through a relationship like this. You may see this relationship here, which is C equals lambda nu. In other words, the speed of a wave is related to its wavelength times its frequency. So these two things, these are all sort of interrelated variables. By the way, speed is not the tap, tap, tap. Speed is how fast does it go from left to right. So the speed of, say, light is 3 times 10 to the 8th meters per second, or 300 million meters per second. So in this case, we know that if this is 300 million and we know what its wavelength is, we could calculate its frequency, something like that. But as one goes up, the other goes down. So basic characteristics of waves. Second thing is, when we expand this out from just visible light, there's a whole wide range of things called the electromagnetic spectrum. I gave some examples earlier that all do the same sort of behavior. They all have wavelength, they all have frequency, and they all travel at the exact same speed. So at one end of this, we can have our red light, which is a fairly long wavelength, and at the other end here, we've got violet light, which is a fairly short wavelength. And those are the parts that we can see. But if you take a look at this diagram, this part up in here, which is kind of wild to look at this, visible light is actually just a really narrow band of all of the different things that are actually called electromagnetic waves. So we've got things like gamma rays, X-rays, and ultraviolet are just on the violet end. They're beyond violet, ultraviolet. They are even shorter wavelength and higher frequency. On the other end over here, on this kind, the red end, so like this line right here would be the reddest light that we could actually see. So beyond red, we have infrared, even longer wavelength than red light. And then beyond that, we have radio waves, and then we can talk about things like cable and TVs. Microwaves are down here, cell phones and things like this are sort of between infrared and radio waves. So that's down on that end of the frequency. And all these things are the same basic kind of thing. They all travel at the speed of light, 3 times 10 to the 8th meters per second. And they all have wavelengths and frequency. It's just a matter of which wavelength is theirs. There's a really narrow bit of wavelengths that we can see that we could call colors, but there's even narrower wavelengths that we call in the ultraviolet and beyond, and then there's even wider wavelengths in the infrared and beyond on that side. The electromagnetic spectrum. It's called a spectrum because they all blend into one another. There's no hard and fast line between any of these. They grade out. So a red light blends into infrared, and then infrared blends into radio waves at a particular wavelength. We sort of cut it off and say, all right, well, now we're going to call this ultraviolet or something else. It's just a different range within that particular set of wavelengths. So visible light, the part that we see is super skinny. Like I said, here it is another way to represent this. Here's that narrow piece that we've got. On one end is violet light, and on the other end is red light, and each of these has their own sort of unique wavelengths. And so here you can kind of see the differences between them. The red ones are longer wavelength, and the violet ones are shorter wavelength, higher frequency. It turns out these are related to energy. So red things, long wavelength lights, low frequency lights, are lower energy. They're not damaging to us. Things on the other end, this violet end, where they're short wavelength, high frequency, those things are higher energy on the end of the spectrum. So if you take a look at this over here, over on this end of it, the violet end of the spectrum, these are the things that are kind of scary to us, right? Ultraviolet causes cancer. X-ray goes through your body. You know you're not supposed to be exposed to X-rays. This crazy looking letter is the Greek letter gamma, or gamma rays. This is the kind of stuff blows right through you. And this causes things like radiation poisoning. These are the high energy end of the spectrum on the violet side. On the other side is the infrared side, or the red side, and these are not really the dangerous. These are the low energy sorts of radiation, or electromagnetic radiation. So infrared, there's our microwaves, radio waves in between there. There's a short wavelength and longer wavelength. And then we even get super ultra long radio waves, which are a different sort of stuff that we don't even use for the kind of communications you're familiar with. But again, it's related to energy, and energy is related to color, and color is related to wavelength, and all these guys are part of that same spectrum. Okay, moving on. By the way, visible light, that little slice that we call visible light, is no different than any other type of electromagnetic radiation. It just happens to be that these two things are only tuned into a really narrow range of wavelengths. And you can kind of see that visible spectrum that we are used to. We can see that. Other creatures can actually see a different range of spectra, a different range of wavelengths can be tuned in by their eyes, and it may look a little bit different to them. So for example, we talked about a dog and what a dog can see or not see. A dog can see actually very similar wavelengths to us. They can actually see more into the ultraviolet than we can. They just don't perceive red as being particularly different as the other types of things that are down in that range. They kind of see yellow and the sort of less yellow going off to that end. If they see things that are truly red to them, it actually looks like a dark spot, almost looks black. They can see it, it just does not glow to them like bright red glows to us. Red's a really important color to humans, not so much an important color to dogs. Dogs can see blue and yellow just fine, not so much on the red range. Other kinds of creatures can see different, like if you're talking about pit vipers. Pit vipers are a type of snakes that can actually see heat signatures. They can see in the dark, so to speak. What we would see as darkness, they can actually see infrared. So in this little bit right here, there's our visible light. Well, they have these organs called pits, part of their little faces, that can actually see into the infrared. And to them, they would see that as a type of a heat signature. So they actually see the trail of a mouse after the mouse is left, because there's sort of a heat path that's left behind it. And bees, by example, just for something else, bees see in a slightly shifted version of us. They see more in the ultraviolet. Ultraviolet light is actually really important for bees and how they see flowers and flower colors. They tend to see more brightly, I guess, in that range than we do. So the blues and the violets and the purples are much more important to them. We tend to see, for some reason for us, yellows and reds a lot of times as being very, very vibrant. So just a different, like I said, different things in terms of our little detectors in our eyeballs, what we see. So just as sort of an aside, I guess. Okay, sort of the last piece here. When we're talking about energy, this is really important in terms of a piece I want you to understand. There's more or less 7 kinds of electromagnetic radiation. Some of them are dangerous to us, and some of them are not dangerous to us. They're not really different in quality, I guess. They're different in quantity. And what we get is this visible light for us is sort of right at the edge of the dangerous spectrum for us. What we can see is not dangerous. As you get into certain types of ultraviolet, and it's, as you can kind of see the little color range here, sort of halfway through ultraviolet and past ultraviolet, this is what we start to get into the range we call ionizing radiation. Ionizing radiation is strong enough, there's enough energy in that light, in those photons of light, that they can actually disrupt cellular chemistry. Typically what they do is they can damage DNA, and that's how ultraviolet can cause cancer. It can actually interact with the DNA of skin cells and cause that DNA to sort of crack a bit, and they lose control of their cell cycle, and rather than behaving like normal cells, they start to just reproduce, and we call those cancer cells. We know that ultraviolet is dangerous, and you probably know that X-rays are dangerous. X-rays are dangerous, yes, and in fact, if you get exposed to lots of X-rays, it will cause cancer relatively quickly. That's why the X-ray tech leaves the room when they go take the button, right, or your dental tech, when they're taking X-rays of your teeth. You're exposed to such a tiny little bit, a quick little flash of that light, that it's not going to affect you, or the chances of it causing damage to you are very, very slim. And they've kind of decided, as humanity sort of decided, that the risk of an X-ray is so much smaller than the injury that you're trying to diagnose. So being able to look at a bone and say, yes, that's broken, or look at a tooth and say, yes, there's a cavity there, you're much more likely to be at risk from the injury than you are from that tiny little flash of X-ray. So again, not so dangerous for us. Gamma rays, way off on the side. That's what we would typically call radiation. So if you hear about people that are having radiation poisoning, that's often that gamma ray end, and that's super ionizing, and that causes lots and lots of cellular damage, and you will die from that with relatively small exposures to that. It's definitely unpleasant. The other end of this, the whole other side of this is sort of our communication side, right? If you take a look at those things that are on there, this is how we actually use light to send information. So not necessarily the infrared, but we're talking about microwaves, radio waves, and all this kind of stuff. This is done on this end. This is non-ionizing. It's not dangerous for us. You are bathed in this sort of radiation right now, but it doesn't cause us any harm. It's too low of energy for it to actually cause any sort of cellular damage. So that's how we can have radio waves all over the place. You ever wonder why that's not a problem? No. But radio waves all over the place. Microwaves are not the appliance, but the actual waves of microwaves are only dangerous because of a particular tweak, a particular trick that certain types of microwaves can make water molecules resonate, vibrate faster, and increase in temperature. In general, microwaves are not dangerous. We use microwaves, that sort of range, to actually transmit cell phone data, that sort of thing, or satellite data. So that's over on that end down there. So like I said, just because it's radiation doesn't necessarily mean it's dangerous. It's radiation on the violet side and the ultraviolet side. That's ionizing radiation, dangerous to life. The stuff that's on the visible light and all the way over on the red end, definitely not dangerous to us. It's just the same kind of stuff. It's just lower energy forms. So coming back, how does this help? Well, I'm not really going to answer that in this particular case. All of these pieces about how light works and how the difference of wavelengths of light kind of feed back into what Bohr was trying to do. You have to understand about light and light waves and wavelengths and energy to be able to understand what Bohr was up to. So he was working on trying to improve his model of what electrons were doing in the atom, and it comes down to this idea of energy absorption and light production. He took a look at this thing, like this picture that's on here called emission spectra, or light being produced by elements, to kind of understand more about electron behavior. And he came up with a really big idea that we'll get to in the next lesson. Going back in terms of this sort of idea of what is light, well, visible light is simply one type of electromagnetic radiation. We looked at some other types of electromagnetic waves and electromagnetic radiation that's out there. And there's this really broad spectrum of things that fall into this category. Again, we're going to focus on light, a little bit in ultraviolet, to help us understand some more about it. But electromagnetic waves is a really broad range of things. They all have the same ideas of wavelength and frequency. They all travel at the same speed, and they all can transfer energy. So these kind of interrelationships is what we're going to take a look at in the next model, or the next lesson, about how do we use light emission to learn more about electron behavior. So there you go. Stay tuned. We'll get to put these on in the next one. Have a good one.